All right. So now we're gonna start with what we were doing, and wait a second. I want to record everything. Wait a second. Let me record it here. I hope the. Okay, cool. So now let's go. So last time I believe we were doing, yeah, pretty much it, right? And I told you we'll start from here. If you guys have any questions from the previous class, please let me know. Okay. I probably want to check something first before we go and start this. Okay. Yeah, all right, perfect. So that's not fair. Okay. Now, so about heating or cooling curves. Now these are not important, right? The reason is that it's optional to draw these, all right? But I would say that if you are drawing that, that's a plus. And the reason why you should draw this is because sometimes you should always, sometimes they help you in, okay, wait. Okay. So sometimes they would help you in getting the answers right. And this is why we're going to look at them. So first of all, we should understand that this is the point where if you're starting from this point and you see the line is going up, it means that the temperature change is showing here. And whenever temperature change is shown, what you can do is you always need to use mc delta theta. And the reason is because obviously in this section the material is getting heated, and now when the straight line comes, so for example in this section, obviously it means that now the temperature is constant, it's staying the same. It means melting is happening. If melting is happening, then you use LF times M, so that would be the energy equation. And then the next section, now the solid has completely melted, so right now it's in the liquid state, so I can say this is where it is liquid, this is where it was solid. So now in this section you're gonna again use mc delta theta because now the temperature is changing. So then you can say, all right, this one, if you look at this one, then in this section you might realize that this is where the boiling is happening, right? And whenever a state is changing, you should remember that the temperature doesn't change. So now this means this is going to be our LV times latent heat, specific latent heat of vaporization times mass, and then you can basically go forward with the other things as well. Now, then the next section, because again in this one it has changed to gas and now it's gaining temperature, which means that you will use mc delta theta. So by looking at this, you can see what stages are there and which equation you should use. So this would be the heating curve and this would be the cooling curve. I'm sorry, I forgot to write it. And when the cooling curve comes, so you should understand that this would be basically gas. This is where it will be liquid. This is where it will be solid. Now, so when the gas is cooled, this is where it is going to be mc delta theta because it's the change in temperature, and then here it's basically causing condensation. All right, So for condensation, you use LV times M, and then again, when the temperature changes, MC delta theta, and when it is constant, you take it as the freezing, right? Freezing or solidification, whatever you call it, it's fine. So latent heat of fusion, and then obviously again temperature change would cause it to have MC delta theta, and that's how you can build it in stages, and that would help you get the idea of overall what's going to happen in the question. Okay, so if you guys have written this, I could then go forward. Okay, right now, so then let's go and check out this question. So in this question, it says a polystyrene cup contains a mass of 95 grams of water at 28 degrees. Ice cube of mass 12 grams is put into water initially. The ice is at 0 degrees. The water of the specific heat is this one. So this is the specific heat capacity, and stirred until all ice melts. So assuming that the cup has negligible mass and there's no heat loss. Okay, so there's no heat loss. All right, that's not good. I don't know where I put my stuff. Okay, never mind. So, and specific latent heat of fusion is also there. Now, what is going to happen? So it's saying calculate the final temperature of water. So we're gonna basically look at that in a heating curve situation. Okay, so what I'm gonna do is I'm gonna build one curve. I could do that with one curve. I can also manage two curves if you want to. It's fine. So what you're gonna do is you should understand that when it all started, the ice, let's make it separate, because then you might get confused. So for ice only, I would say that initially it was, for some time it was melting at 0 degrees, and then obviously it would have changed its temperature when it has converted to water, and that's when it has reached an equilibrium state, and that is the temperature theta that we need. So this is temperature in degrees Celsius, and that's the energy in joules. Okay, so now in this section I would just tell you this is when it is solid, it's melting, and this is where it is liquid. And for the other one, like water, I would say let's build it here. Okay, so you can do it on one, only one of these, that's fine as well. So for water, what I'm going to do is, the water temperature initially was 28 degrees, right? So it means that it was somewhere here where it was 28, and now obviously water would have cooled to some point where temperature theta is where the equilibrium has reached. Okay, now by doing this, now I have a clear understanding what is the question about. So I'm saying whatever the heat gained by ice is going to be, that's going to go to the heat that's going to come from the heat lost by water. Okay, so now what are the stages of ice? Now I can see it was melted, which means I need to use latent heat of fusion times mass, because that is the section. Let me just write latent heat of fusion times mass, and then it was also heated, so I'm going to use MC delta theta in the liquid state. So there are no other stages in this, but on the other hand we have just water that is being cooled, so I can say that it's going to be MC delta theta, because clearly I can see the line is now flat, and now I can use this one. Now let's put in the values and try to find out the end theta. So first of all, latent heat of fusion of ice is given in joules and kilograms. So I'm going to write 3.3 times 10 raised to power 5 times the mass of ice was only 12 grams. Because it is in kilograms, so I got to change that. So if I change that, it's going to be 12 divided by 1000, because I want it to be in kgs. Okay, then plus this mass m is the same mass when ice was, melted to water. So I'm going to use the same 12, and I'm going to see, because the heat capacity of water is also in kg, so I'm going to divide it by 1000. Sometimes it's, if it's not, it's all right. We're going to write it 4.2 times 10 raised to 3. Now you might be wondering, why am I, multiplying water's heat capacity in, ice section? Because now ice has fully converted to water, so we need to apply to that. Then the temperature that ice gained was from the final temperature it reached was theta, and from 0. Okay, so then the next part of the equation is going to be the mass of ice, which is 95 grams. I'm going to divide it by 1000 because our heat capacities are there in kilograms. So we're going to write 4.2 times 10 raised to 3. And it basically goes from 28 to this. Now, I would like to tell you something very important here. And that is, let me change the color. And that is, just remember, always in scalar quantities, because temperature is scalar quantities, always in scalar do larger minus smaller, and that way you will always get a positive value, because that's how we should be doing with scalar, because we are not, we don't need a direction, so negative positive sign doesn't really matter. So now from this point onwards, this particular section, we're gonna solve it out. We're gonna say, all right, this is going to be 3.3 times 10 raised to power 5, and that gets multiplied by 0.012, right? So this is going to be 3960 plus, this is going to be 0.012 times 4.2 times 10 raised to power 3, and then 1 is 0, so it doesn't really matter. So this makes it 50.4 theta equals to, the other one is 0.095 times 4.2 times 10 raised to power 3. So that's 399, and if I multiply 399 with 28, I'm gonna get 11172 minus, and then obviously 399 theta. Okay, so now bring the thetas together. So it's going to be 3960, yeah, so that, bring it there. So it's going to be 50.4 theta plus 399 theta equals to 11172 minus 3960. So let's try it, solve this. So we're going to subtract this from 3960. This is going to be 7212, and that going to be 50.4 plus 399, which is 499.4 theta, and theta is going to be then 7212 divided by 499.4, which basically is 14.4 degrees Celsius. So I'm just going to write that. Do you guys understand that? And obviously this takes a lot of time to solve these, so you are supposed to then just chill out, relax. All right, you will be able to get it at the end. All right, any questions, please? Anything you'd like
So I
to?
got 16 degrees Celsius.
You got 15, Gatika. That's not fair, Gatika.
15.
15,
So 16.
16 with the same calculations.
Yeah.
Oh my god, that's not fair. What did I
Sir,
get
your
wrong?
value is wrong.
Which value?
Sir,
499.
yes,
That's
sir,
wrong?
it's 449.
It's, oh,
Yeah.
okay, sorry. Okay, thank you people for 449. Okay, so this would be 16 degrees Celsius. So I'm gonna write 16 here. All right, who did not get it? Do you guys understand the use of cooling curves and heating up? They're not required by the question or the examiner. It is just a tool to help you understand that which equation you should use where. Okay, is it clear?
Yes, sir.
All right, that's pretty good. Okay, so then I'm gonna go to the next question. But before that, I just need to ask from you people. Can you guys just wait for 1 second, please? I'm coming back. I need something. Okay. Now, so then we are going towards, obviously, the next question would be this one. And I think you guys can do it pretty easily. So that should be your homework. And then, yeah, this is also the same. You should be doing this homework. This is the same question. Please try to do this. This is like a breakup of the previous question that we've done. Right now, we are going to go towards the determination of specific heat capacities. Okay. So, my buddies. So, the first question, it basically asks you that we want to find the student states strongly with temperature. That temperature measures the amount of thermal energy heat in a body. Okay. So what? So then it says that. So it says that we state and explain two observations that show why this statement is incorrect. State and explain. Okay. All right. So as far as student states quite wrongly that temperature measures the amount of thermal energy heat. Now why you should never think that temperature is heat. Okay, so this is something very, very important to understand. The first thing that you should always remember is that these two quantities are entirely different things, right? So we could say, although they're interrelated, but they're very different. So we would say that two objects, all right, of maybe different masses at same temperature would contain different heat energy. And the reason why that would be important to know, because you see, if you heat a metal to 100 degrees and if you heat water to 100 degrees, obviously metal will heat up quickly because it needs less heat energy to raise the temperature. But then water heat capacity is larger, so it needs greater energy to reach the same amount of temperature. So you just need to remember that, all right? The other biggest thing is that you should always remember that at changing of state, right? Although heat is absorbed, right? Or released. So whatever is happening, right? But the temperature stays constant. And that is the reason why we would say these two quantities are quite different. Do you guys understand this? Any questions? Yes, please. Okay. Change. I want to.
No, sir.
Okay, perfect.
Sir,
Yes, please.
what are you written in the second point? Changing of?
Changing of. I have written. Where?
Second point.
At changing of state. At change of state.
Okay.
Sorry. I want to write at
I
changing
don't
state.
understand this question.
You don't understand this question?
No.
Gatika, when suppose what I'm saying is, why do you think that at the same temperature, like the bucket, let's suppose this is the steel pan that you're heating water in, right? Why do you think this heat pan gets to the same temperature as water earlier than water itself? Why do you think like that?
Because it has lower specific heat capacity.
So it means that at the end, if they have the same temperature at the end, the metal would require less amount of heat energy to raise the same amount of temperature as water. Do you agree?
Yes, sir.
Then, if that is the case, then what do you think would be? Why do you think then temperature is the same, but they contain different amount of energies, like different amount of heat energy, so they cannot be the same thing, right? Is that clear?
Yes, sir, got it.
Yeah, and the other evidence is that when the change of state is happening, which means either it's melting, boiling, freezing, or condensation is happening or whatever. At that time, heat is being lost to the surroundings, or the surroundings are giving heat to the system. But does the temperature change? No. So they could not, be something that you can interrelate with. All right, is that clear?
Yes, sir.
All right. So now, when you want to determine the heat, the heat capacity of any solid, this is the system. Now, why I've captured an actual picture? Because the reason is that one, I have no good drawing. The second thing is I wanted to show you that in this particular picture, what you do is, if let's suppose you want to find the aluminum block heat capacity, you insert a heater. Now, heater symbol, this is for paper 5 only, and I'm just telling you, heater symbol is like this. All right, so this is called heater. You should know from AS, and obviously you need to, it says electrical connection, but in paper 5 you need to physically tell them what is positive, what is negative, and a voltmeter should be attached, an ammeter should be attached, and something like that. So that would, in the paper 5 you should show the complete circuit. Is that clear? Okay. The other thing is that usually what they do is, what we want to do is that we want to add some insulation as well. So when you add insulation, insulation basically helps reduce the energy loss, right? So you want to add that insulation as well. That would be something you should remember. All right. Now, so in this particular question, it says the power rating of heater is 54 watt, and the heater is switched on, and the readings of the temperature of the block are taken at regular intervals. Now, again, these regular time intervals, with respect to paper 5, I'm just saying take it as 5 minutes, because the examiner thinks that's the standard and we should follow that. Okay, although it doesn't make sense. All right. Then says when the block reaches a constant temperature, the heat is switched off and the further temperature readings are taken. The variation with time temperature block is shown just like they have done it. Okay. Now everybody understands the question. Should I move to the next slide, please? Okay. So then it says, suggest why the rate of rise of temperature of block decreases. Suggest why the rate of rise of temperature of the block decreases to 0. Okay. Now, the thing is that most of the people would write that it starts to melt, but that's not true. The reason is that because there was no insulation, so if this thermometer is providing heat to the block, but then the same amount of heat is being lost to the surroundings, then obviously it would reach sort of an equilibrium, right? Where now whatever heat you're getting, that's also escaping, which means now the temperature rise would not increase. Do you guys understand? So, the best possible way of writing this would be that for 2 marks, I would say that when temperature, sorry, when heat gain by block is equal to heat lost to surroundings, right, by block, then uh, the temperature rise would stop, okay, due to loss of energy, and you can also write dissipation of energy. Or anybody who could not understand this, please let me know. Okay, so where I was, Anusha, Suman, Mokshit, Gatika, Juveria, Ahmed Zaid. You guys understand everything?
Yes, sir.
Okay,
Yes, sir.
that's pretty good. That's pretty good. And Aman, do you?
Sir, what do you mean by the second point? Could you elaborate on that?
I just mean that I just explained that what is the temperature, the heat loss is. So heat loss is basically something that the amount of heat that's going out to the surroundings, okay, from the system. Do you understand? I just need to explain that.
Okay, sir.
Okay. Then says after heater has been switched off, the maximum rate of fall of temperature is 3.7 Kelvin per minute. Estimate the specific heat capacity of this. Now, so you should understand that what are we doing, all right? When it reaches to a certain, level where it is at equilibrium, so we can say whatever the input power is, that would be equal to the minimum rate of heat loss, right? So this is basically at when the temperature stops rising. So we want to find the heat capacity. That's fine. The power of the heater, the maximum power is already given somewhere, I believe. The mass is 960, power is 54. What else do we have? We have nothing else. Okay, pretty good. So the power would be 54 watt, and because there is a change in temperature, so we're going to use mc delta theta, and obviously this is energy, so we're going to divide it by time as well, because we want to basically see that how much the energy is changing per unit time. So now 54, the mass was 960, so it's going to be 960 because it needs in kg, so we got to change it. Heat capacity, the change in temperature is basically 3.7 Kelvin, and that is happening in 60 seconds. Because this is in minutes, you got to convert it to seconds. Can you please find this? Because now that I've demonstrated that I'm incapable of calculating. Yes, please. Okay.
So 912.
912. So 912 joules per kg per Kelvin. So that's going to be your answer. You can also get away with writing this, or let me just write it here, 910. Okay, because that's correct to two significant figures, and he has given the same amount of data. Now, if you write 900 or you write something bigger than that, bigger than 912, number of significant figures, then it would be wrong. So please do remember that. Okay, any questions now? All right. Okay, for some reason. Okay, so then let's go to the next question. So, yeah, so for her, I hope you understand this. And okay, and who else is with us? Anusha, Moksha, do you understand? Saman. Okay, everybody does. That's pretty good. Okay, and Arsalan, everything is clear. Munib. Okay.
Yes, sir. Yes, sir.
Now the next thing is the determination of specific heat capacity in liquids. Okay. Now I just want to tell you it is done like this. There is basically water in, there is water out. I just want to tell you a couple of things here. First of all, you should understand that the temperature change. So let's suppose that water in was at T1 and water out was coming as T2. So when we repeat, all right, we must keep T1 and T2 temperatures constant. So that's something important. All right, so drawing is overall this, and obviously when you have to draw it for paper 5, you also need to connect it to a power supply, and then you need to connect it to voltmeter and some ammeter. You can also add a resistor if you want to, keep the current low, but that's up to you entirely. Anyway, so I'm erasing this a bit, and then we're going to move forward. So first of all, it says two metals are in thermal equilibrium. So this is the one from the previous topic. State and explain what is meant by thermal equilibrium. Thermal equilibrium means that both bodies are at same temperature, right? And there is no net. Writing net is the keyword, net flow of heat, which means neither of them have different heat, right? So they can exchange that, but that should be at the same level. Is it clear, everyone? All right. Now, wait a second, please. Now, these sort of questions, in this one, it says water flows into a tube at 18 degrees, and when the power of heater is 3.8 kilowatts, the temperature water outlet. So this is T1, this is T2. The specific heat capacity of water is given like this. It is in grams, as you can see. Be very aware of that, and use the data to calculate the flow rate. Where's the data? I don't know. We just need to basically calculate the flow rate of that. We can do that, I think. How though? All right. So we know power into basically power into time is energy, and the energy we are giving it is basically equal to mc delta theta, right? So the power is 3.8 times 10 raised to the 3. Time is what? Time we need to find, right? So yeah, we just need to find flow rate. So we're gonna do time here, and then this is going to be, time could be just 1 second. All right, let's put it 1 second. All right, so we can find the rate. The mass of, we need flow rate in mass over time. Sorry, we can't put it T. So let's write M here. C is given as 4.2, and the temperature change is obviously 42 minus 18. So what do we need? We need mass flow rate, which is mass over time. So for that you need to do, I think, 3.8 times 10 raised to the 3 divided by 4.2. multiply by 42 minus 18. Can you find the answer, please? Yes, go on.
37.7.
37.7. All of these are in two significant figures, so we can write it as 38 or 37.7. That would be correct as well. Anyway, now it says state and explain whether your answer in one is likely to be an overestimate or an underestimate. Okay, now this is a very important, part. So yes, please go on. Please tell me that.
Overestimate.
So overestimate probably.
Okay, so what's happening here? We need to understand that the power of the heater not only basically goes into, like, the energy goes into the water, but also some energy is being lost because it is not, entirely isolated, right? Insulated. So which means that the power of heater is going into two things. It is going in heating of water plus heat loss to surroundings. So this is our equation, right? Now, when you ignore this, right, you should understand that now we're assuming that all of the power is going into this, which means that the power value of taken right here is bigger than it should be. Is that clear, everyone? So naturally, it would be an overestimate because in actual the power received by water would be less, which means that the flow rate is going to be smaller value. All right, the power estimate is it is an overestimate because there would be heat loss to the surroundings. All right, Arsalan and do you understand? And Munib, Suman, and who else is here? Kartika, Javeria, Mokshit, Aman, Anusha, Ahmed.
Yes, sir.
Today
Yes, sir.
Tanjim Ahmed is not here. Why is he not here? Strange, you know? Wait a second. Okay. Okay. All right. So now let's go to the next part. This question I left it for you, so this is your homework. So please mark on your PDF as well. Okay, and then we're gonna go forward. Now, the next thing we should do is the latent heat of vaporization. And the first part of this is that they want us to explain. Yeah, so they want us to add to this one specifically fusion. So we're going to write it in general terms. You're going to write it is the amount of heat energy per unit mass, because it is specific, per unit mass to completely change state without changing without change in temperature. So that is how you're going to get 2 marks for this. All right. Now, so then let's go forward and check what is the question about. Again, in this section, I just want to tell you what happens is it is
Show the definition.
yeah. So this is pretty easy. Actually, the real drawing of this is that actually you put a pan balance, right? They've also written pan balance. What pan balance does is that as it is heating, the water basically boils, and the value of mass right here keeps on decreasing over time. So you can fix some time, like 5 minutes or something, and you can check at regular intervals, like after each 5 minutes, that how much mass has gone out. All right, and then the difference of mass gives you basically the mass over time will give you the rate of evaporation, sorry, boiling. So that's pretty easy that way. Anyway, now in this particular question, you've written it. Should I go forward, please?
Yes, sir.
Okay. So now let's go and look at what's happening here. So right now they have given a graph after taking different times, and it says state the feature which suggests the liquid is boiling at a steady rate. Do you guys know what is that feature? Rate would be mass over time, right? So rate would, yeah, mass over time would give us gradient. So that would be the gradient of the line, right? So that's easy. Then it states that use the data from the figure, determine the specific latent heat of vaporization. Now we need to understand something very important. Specific latent heat of vaporization is Q equals to LV times M. That's what we have taught, right? I've taught you. So this is power into time, LV times M. So what do we need? We need this length, this L. So let's write it L. Power, I don't know. Do we have the power? Yes, we do. It's 110, right? So I'm going to write 110. And you can basically pick the time. You can pick the gradient, really. If you understand this, it's going to be T equals to L times M. If you notice, we can basically find mass over time, which is actually the gradient of this graph, which she has asked initially. And from this equation, we can write it as 110 equals to L times mass over time. So if I put in gradient here and divide by 110, obviously I will be able to find it. So you can pick the time that suits you. So I think this part is easy, which is right somewhere in the, I think it's not entirely the middle, I don't know. So this would be, I think, 330. So that's going to be 332, right? And the start, when the time had not started, this would be, okay, so that's going to be 370, 372. So the change in mass is going to be, let me do it here, 372 minus 332, and that 2 happening in 6 minutes. So 6 into 60 I'm going to do, because I'm going to change it into seconds. Can you please find this? Yes, please.
0.11.
0.11 grams per second. Okay, because we need it in kilograms, unfortunately, so we got to change it further. So 0.11 times 10 raised to power minus 3. Now it is in kg per second. So I'm going to put it back, and I'm going to write 110 equals to latent heat of vaporization times 0.11 times 10 raised to minus 3. Can you please find this then? Yes, please. That's so much time. That's not fair.
It's 1 million.
1 million? Oh,
So 1.0 times 10 power 6.
okay, so it's gonna be 1.0 times 10 power 6 this. All right, something I would like to tell you, which is very, very important actually. And that is that you guys should always, remember. Wait a second, I need to, it's strange. Okay, the thing that I would like to tell you basically is that you should understand never, ever, never, ever take small triangle. Okay, in any case, like some people would feel, okay, this is an easy point, so why can't I take just this point and this point or something like that. Make sure that when you're taking 2 points, they should be at least, and that's for paper 5 as well, at least 50% away from each other. So that's a tip that you should always follow in many questions, and usually if you do not do that, you will get penalized. Okay, is it clear? Okay, now then it says state with a reason whether the value determined is likely to be an overestimate or underestimate normally accepted value from the specific latent heat. What do you guys say? Yes, please.
Overestimate.
Overestimate. And the same answer would be like the previous one. It is an overestimate because the heat is being lost to surroundings, as well as obviously things are like they're going out. All right, so you just need to remember that. Anyway, now if you've written this, please let me know so I can go forward. We just need to do one more thing and then we're done. Okay. Done. Should I go forward, everyone? Okay. Then we're going to look at this particular question, and that would be the last one for today. No, this is your homework. I'm sorry, that's the same question. We're going to go for this question actually, and that is the determination of specific latent heat of this. Again, you have to write the same definition. You should write it as homework. But then this question. So this question is when we are actually finding specific latent heat of fusion. Again, what you do is you put a pan balance here, and the reason we put pan balance is you want to find how much water mass is collected when you melt it. Like basically we leave it to melt on its own from surroundings, right? And the reason we do that is because we want to find how much mass melts because of the surrounding. And then what you do is then you turn on the heater, check how much mass has melted, and because the difference between these two would be that, let's suppose this is mass m, that was melted because of the surrounding, and this is mass capital M, that is when the mass was melted after the heater was on. So what you should remember is that the mass melted by heater would be equal to this minus this. The reason is because this one basically is the mass that is melted due to heater, also due to the surroundings. Is that clear? All right, everyone. Okay. Now, the other thing in this one is, and specifically in this one is, that usually the equation for latent heat of fusion of ice is a different one. In this one, we take heat from surroundings, okay, because we're getting heat from the surroundings, not being lost, plus heat from heater, that goes into latent heat of fusion times the mass. Do you guys understand this? Everyone? Okay, great. So now in this one, they want us to find this mass rate. This is in like mass melting in 5 minutes. So 5 minutes would mean that we got to divide this by 78, divide by 5 into 60. What would that be? Because we need it in seconds, right? Yes, please.
0.26.
0.26, and this one would be 114 divided by 5 times 60. That would be
0.38.
0.38. Okay, then it says complete the it says complete the mass melted per second, blah blah blah. Use the data in this to determine the value of fusion of ice, right? So now again, we need to understand that this is what the change in this is. The change is that the power basically changed this. So what are we going to do? We're going to find the power into time equals to latent heat of fusion times mass. Now by taking the change, we are doing this one. So we already have the mass melted, and how would we do this? We're going to use 110 minus 70, and then we're going to multiply it by 5 into 60 because it was turned on for 5 minutes. We want to find this length, latent heat, and now we're going to subtract the mass too, because this would basically eliminate the heat that is coming from the outside. So could you find this, please? That would be, hurry up people, it's only 5 minutes left for the other class.
One times 10 raised to power 5.
Okay, whatever. Let's write it down. Whatever Gatika says is correct. Okay. Then it says the rate of thermal energy. Now you can pick any equation. Like you can pick this one, this one, this one. And you can say, okay, power into time plus the power that was from the surroundings, okay, in this time goes into latent heat times the mass, right? So first of all, power into time, you can take 70, and we want to find this rate. The latent heat we have found as this one, and the mass mass rate was basically 0.26. Now can you find H, please?
So the answer for L, it does not match the marking scheme.
What is it?
In the marking scheme is 330.
Really? That's not fair. What, did you guys make a mistake or did I make a mistake? That's an interesting thing, right? Oh yes, it could not be matched. I understand why. The reason it cannot be matched because I think the power was in SI units, but our mass wasn't in a SI unit. So to do that, we need to divide by 10 raised to power minus 3 actually. Can you try now? 40 into 5 into 60. divided by 10 raised to power minus 3. And what? Gatika, that's not fair.
Sir, I think because you've used 5 times 62, you should use the mass which melted in 5 minutes.
No, I basically made a I made a error here. Already we had like basically this was mass per unit time, so I should not have multiplied with time. This should be only power because already it's mass unit time. So that's one mistake that I've done, and then I have basically not converted it as well. Now, can you, Gatika, do it again, please? Try now. I think should be fine now.
So without 10 raised to minus 3, it's correct.
Yeah, without 10 raised to minus 3, it is correct. Are you sure? Oh, yeah, it is in grams. That's fine. Fine. Okay, 330. We don't
तो
need to
आपने
change.
change क्या किया था?
I changed it to kgs.
No, what did you change in the calculation?
Earlier, oh,
Yeah.
what I did was basically I put the right equation, but I failed to realize that actually the mass is already in mass over time. So my equation should have been power equals to latent heat of fusion times mass. That time divides here, so it's all right not to multiply time already because we have already done it here, and that's why. Is that clear?
Yeah.
330. So we're gonna add 330 here. Now can you please find H? I think it should be somewhat like 20, 25, I don't know, something like that.
15.8.
Oh, cool. 15.8. So that should be 16 watts. Do you guys understand this? Everyone. Okay.
Sir, could you explain the second question again, please?
Can I do what?
Explain the second question again.
Okay. So like I said, what I've done is you should understand that power of heater plus power that we receive from the surroundings, they're all helping in melting this mass. Do you understand?
Yes, sir.
So what I did was I used one of the equations, like I used 70 when this power heater was this, and we don't know what is the power of the surroundings. We call that H, and this was like we already found latent heat of vaporization, fusion, and the mass was this much. Mass flow rate or mass getting out. Okay, is that clear? So then I had to solve this.
Yes, sir.
Yeah.
Oh, okay.
Okay.